Section 5.2, page 1, the definite integral. So we had previously discussed finding area under a curve, specifically a positive continuous curve. And we did this by breaking the curve into various rectangles, a different amount each time possibly. And then we added up the area of each of those rectangles, where delta x was the width of the rectangles and the output of the function was the height, but we had used notation to represent the different sides of the rectangles and, whether it was left, right, etc. So now what we're going to do is talk about curves that can have negative area, and there could be discontinuities, but what we'll focus on first is the new notation, where very specifically it's to represent the net area. So we'll begin with the definition of the definite integral. So f needs to be a function that is defined on some closed interval from a to b, so we don't necessarily have a discontinuity yet. And what we'll do is we're going to look at this function from starting point A to ending point B, and when we evaluate the definite integral, we're going to end up with a number. Now, we've also been talking about antiderivatives, which end up with a function, but we're going to be taking a definite integral to end up with a numeric value. So here's the notation that we'll break down a little bit further, but hopefully you remember the integral notation that we had shown before. Well, now we're always going to put our x starting point value at the bottom and our x ending point value at the top, and then still list our function dx. And we're still going with the concept that we're adding up a bunch of rectangles where the rectangles are the width times the height. And if n goes to infinity, meaning we have an unlimited number of rectangles that we're adding up, we're essentially at the definite integral. Don't forget that we had used delta x to be the range of the interval, so b minus a, and then how wide did we want each rectangle, or really how many rectangles did we need. X sub I was all of the different x values that we were plugging in. So we started at the very first point and we moved across with I once, twice, 3 times, etc., as I is being iterated through every value to n. Keep in mind, we often might refer to our function as being integratable if the limit exists. So example 1, I'm asked to just express the following limit as an integral. So this is the answer I'm looking for, but the key was I was only given the limit notation for my definite integral, where even though this goes from 1 to n, don't forget I'm focused on what is the range that I'm looking at the function on, from 1 to 3. And then the function itself is I'm taking whichever x value I have at the time and cubing it, so I don't really need the subscript. 1 divided by the x value is then subtracted from that, and the width is delta x. I don't know if you remember back in differentials, we talked about delta x and dx actually having the same value. So a limit of sums of rectangles looks like what I just circled. The definite integral form looks like what I just boxed. And so again, we're just taking the notation from above and kind of isolating it. But the other piece I mentioned is that this is representing the net area. When we were taking rectangles before, we were just taking these rectangles like this, and we only looked at the rectangles that were above the x-axis. But it comes to a curve. Actually, if you're doing a definite integral, we're not doing rectangles, we're just shading, and you're going to shade from wherever you are on the curve to the x-axis, which could be shading down or between the x-axis up to the curve, however you want to word it. But when you're above the x-axis, your area will be positive, and when you're shading from your curve to the x-axis and you're shading up, or maybe you want to think of it as shading down, but the area is all below the x-axis, that will be considered negative area.